Okay, all right. Let's start. I hope it's not too much annoying today. Maybe I can reduce a little bit sound. Okay. All right, so how are you today? Nice, yeah, nice day, finally. Sunny and it's nice. Okay, I'm returning, so that's very important for me. Okay, oh, one thing I noticed in sort of looking through all your homework one, not many undergraduate students actually know the editorial, function of the Word, MS Word. I would assume you're using Microsoft or word processing. Some of you know, but some of you don't, probably didn't have opportunity. So I just wanted to review. So, oh, by the way, what is PPF? Yeah, photosynthetic photon flux. And then below that, it's a unit for PPF, but it's not really in a professional notation or format. But I have seen that many students, undergraduate students particularly, use this. U instead of micro, okay, that's not micro. So you got to use micro. And how to type micro? The one I recommend is type M, okay, and then select symbol font. So there is a symbol font. SSSS symbol. There you go. The nice micro comes up, right? There's also another way to insert symbol, but I like changing symbol font because it's quicker, So this notation, exponent -2. So I think this is a computer tag or something, wasn't it? You use this a lot in computer programming, as far as I remember, a long time ago. So that's not, the style we recommend, right? You have to use superscript. And then also some students didn't even bother doing anything. So what you do is, basically, you eliminate that, right? And then you select the -2, and then here is the superscript. Here is a superscript, okay? Then you can express in a professional way. All right? Okay, so I just wanted to do quick because you probably had opportunity or will have opportunity to learn all these things, but since I noticed. Okay, any questions? All right. Okay, so what I do is I'm going to go ahead and start talking about photoperiod today. Small. Not showing. Okay. All right. So the handouts. Okay, photoperiodic response is very exciting in controlled environment agriculture. Do you know why? No. And then it's ignored almost, not quite, but ignored a lot in open field production. Photoperiodic response is pretty much practiced or translated into a practice in controlled environment agriculture because we can control photoperiods independently, without worrying about temperature, without worrying about light intensity. We can control photoperiods to induce some, plant response, particularly flowering is a big response. Outside in the field, photoperiod always comes with temperature. When temperature is high, usually long day. When temperature is low, usually, short day, winter time. So you really cannot separate photoperiodic response and temperature response. So the field crop evaluation is always on-site regional. What varieties, what planting cycle works in that particular site, having that temperature, oscillation, having that photoperiod, depending on the location. Okay, so that's why not much information developed in the outside in the field crop production, but a lot of information in greenhouse crop. So I'm going to go through that today, okay? All right, so 2 reading materials. One is Hanan's photomorphogenesis, 20 pages or so, a little bit less than 20 pages. And then the second one is much easier to read. It's the growers' articles, or articles toward growers. Eric Ranko and Paul Fisher wrote this 2004 for growers. So several pages just to get the sort of summary of photoperiodic response. I use a lot of information from their articles because they are the top, top runners in this area, photoperiodic response science in application. So anyway, so those are the 2 reading materials already linked in the D2L. Okay, so we are talking about light environment for the plants, and then we talked about temperature, effect, and photosynthesis, pretty much focused on photosynthesis last week. And then we talked a little bit of, light quality affecting morphogenesis or morphology. So today is a duration of photoperiod. And since we have a 24-hour cycle, photoperiod duration basically refers to also the nighttime period, right? Because 24 hours, when day length is 16 hours, night period is always 8 hours, right? So it's sort of a hand-in-hand situation. Okay, so duration of light period or dark light period. Okay, at 24-hour cycle as an environmental signal for the plants. Many plants use this as a signal to change the direction of growth, whether start flowering or not flowering. And then also another important response of the plant is tuber formation, like potato, tuber formation often triggered by short day. And then also dormancy. Going into dormancy, which is not just photoperiodic response, but also combined effect of temperature and photoperiod. Okay, so there are multiple very important key plant responses, triggered by photoperiod. And because of the importance of knowing photoperiodic response, the plant responses to photoperiods are classified into several categories. One is short day plants, next one is long day plants, and the third one is day neutral plants. And how many of you never heard of those terminology? Short day plants, long day plants, day neutral plants. Everyone have heard. Okay, good. But probably you don't know there are 2 different responses within the same, the short day plants or long day plants. One is qualitative response. The other one is quantitative response. Okay, so that's basically what you are learning today. It's really interesting because you understand the response and then you see the application. All right, so big driving for understanding photoperiodic response, of course, floriculture crop, because you got to induce flowers at certain timing to get the highest value of the flowering crops. For example, poinsettia, poinsettia needs to have that big yellow leafy, structure, which is actually bract, which is not exact leaf, but anyway, so that needs to be developed at certain timing. And then the certain timing you can think about before Christmas or the holiday season start, right? So to do that, you have to impose flowering, and natural environment does not necessarily trigger the flowering response of the poinsettia. Same thing for many crops in floriculture. if the natural environment is not ideal for inducing flowers or suppressing flowers, they have to do otherwise. Okay, so that's why a lot of information. When you go to roads or gardens, centers to find your next, planting materials, your garden, you probably want to see flowers, not just picture of flowers. And then that would add value to your crop, to the crop. So that's why controlling flowers and then finding out what kind of conditions trigger flowering is very important, and then created a huge knowledge base in floriculture, ornamental crop industry. Okay? Remember the greenhouse, majority of greenhouse in US is floriculture, ornamental, right? So those are the users of this technology. All right, so this is a slide provided by Michigan State University, Eric Ranko Group. He is a professor there, horticulture department. They did a lot of study looking at very different species, different varieties, photoperiodic response. What photoperiods actually trigger flowering or not flowering. Challenge of floriculture species is that so many new varieties coming in every year because one variety doesn't last long. It's always, consumers or customers looking for something new, something more exciting. So that's always, driving the need of finding out what is the exact response. So a lot of information as a consequence in that industry sector. But anyway, so this is a Campanula. This is a perennial crop. So the process involved not just 1 year, but multiple years. But when you need to trigger flowers of Campanula, you have to play with photoperiod. And then this is showing multiple different photoperiods from left, 10 hours, 12 hours, 13 hours, 14 hours, 16 hours, and 24 continuous lighting. Okay, out of 24 normal cycle. And then you see that no flowers up to 14. Okay, and then you see flowers when 16 hours or longer photoperiod provided. So this is showing that Campanula is long day plants, right? Flowering at photoperiods longer than certain threshold. So that's a long day plants. We have that definition somewhere written there in the slides. Okay, so short day plants, long day plants, and day neutral plants. Those three big categories. Under short day plants and long day plants, there are two further subcategories. One is qualitative response, so the qualitative short day plants, which is also called obligate short day plants. And then the second one is the quantitative short day plants, which is also, Courtney, do you have? Oh, extra, okay. All right, just keep it, yeah. So the quantitative short day plants, which is also called facultative short day plants. Same thing for long day plants. I'll explain what those, qualitative response and quantitative response are. Okay, so just to start with simple classification, short day versus long day. So this chart's showing flowering percent, okay, so that you start imposing flowers using a photoperiods. And then this chart is showing which conditions, that this particular plant's flower. And then long day plants typically have this kind of curve. So at certain photoperiod, the responses changes dramatically. So the photoperiod longer than certain critical photoperiod or critical day length, flowers, so that's long day plants. Opposite response, so the short day plants flowers under the short days shorter than certain critical photoperiod or critical day length. All right, so there are two sort of mirror image response. And critical day length or critical photoperiod is species specific or variety specific. So having finding that is very important to develop technique, as you can imagine. Whether it needs 12 hours or 16 hours to trigger photoperiodic response, it's very important. Okay, TJ.
Is the labeling or relative?
Yeah, so it's just random. It can be, yeah, it can be anywhere. It can be anywhere. So the next one doesn't show. Okay, let me skip to this one. So this one is all short day plants response, and then so the horizontal bar is the critical photoperiod of different species: aster, chrysanthemum, stevia, carancho, poinsettia. So the poinsettia's critical photoperiod, this is a short day plants, 12 hours, 15 minutes or so. Carancho is 12 hours and 30 minutes. The long one is aster, 15 hours and a half, right? So it's depending on the species, okay? And by the way, this graph is showing the relativeness of the critical photoperiods to the day lengths, natural day lengths from January to December, okay? And in different locations. But anyway, so back to this. Yeah, so critical photoperiod, this value could be any number, okay? Yeah.
They're not flowering after the line, they're flowering.
That's right. That's right. Yeah.
For the short day before the line, they're flowering after the line.
That's right. That's right. Exactly. Exactly. Yeah, some students in the past misunderstood that anything shorter than 12 hours in flowering are short day plants, but no. The threshold doesn't have to be 12 hours. It could be any hours. It's just the response, whether it is, promoting by short days or the long days. Okay. All right. So the natural photoperiod changes, and then that's pretty much determined by, your latitude, right, where you are located. So this one is latitude shown in the United States, and then this is a natural day length over the 12 months period. So we are 32 degrees, right, latitude in Tucson. So if you follow the line between green and blue in this one, you kind of see, where we are during the shortest day and the longest day in June. And then you can actually compute that. If you are an engineer, you can easily find the equation. It's not an easy one, but you can find the equation and type in, your latitude and then generate that sine curve. So this is what I did long time ago. So the Tucson, 32 degrees. So the longest day is a little bit longer than 14 hours. June, and then shortest day is a little bit less than 10 hours. So that's our day length. So back to this slide. So what it means by selecting plants and expecting flowers. So okay, so I'm gonna use a new tool. Okay, there you go. All right, clear. So we are in 30, right? So where am I? 1. Oh, is that 39? Like that? 1, 2, 3, 4. Oh, gosh, no. There you go. So that's us, okay? And then, so if we are growing, let's see, chrysanthemum in Tucson, okay, chrysanthemum, the critical photoperiod is 14 and a half hours. Okay, if we are starting chrysanthemum from cuttings, those chrysanthemums usually start from cuttings, not from seeds. Start from cuttings and then start growing them. And then our photoperiod never exceeds the critical photoperiod. So that means this is a short day plants. So under our conditions, chrysanthemum plants always flower. Okay, always flower, regardless. Because our photoperiod never exceed this particular chrysanthemum, different varieties, different photoperiod. But this particular chrysanthemum listed here always flowers. Well, if it is outside, temperature is another factor to slow down. But let's say you are growing in a greenhouse, nice temperature maintained throughout the year, then it always flowers. If you're growing stevia, okay, in a greenhouse, the time you get flowers or initiating flower is what? Somewhere starting from, so the stevia photoperiodic, critical photoperiod is a little bit longer than 13 hours. So in Tucson, the shorter day starts than 13 hours starts around August. Okay? So that's the time stevia start, developing flowers. And then if your temperature is right, then it can flower during winter time, but wouldn't stop, producing flowers. I mean, would stop producing flowers in sometime in April. And then they never flower during summer. Unless there is other condition trigger that. Yes?
How light does it have to be before you consider the light, the photoperiod?
How light? Meaning the intensity?
Darkness?
Yeah. So the plants actually sense very, very low light. So I'm going to show you probably the next one. Oops. Let me clear the stuff I wrote. There you go. So this one is showing the light intensity that plants can sense. So this is a long day plants, also Michigan State result. And they tested artificially extended long day in a greenhouse, okay, by adding, I think it's like 7 hours additional lighting, if I remember correct. And then, but light intensity was different. So they tested, of course, 0, so the no extension, so there's no flower. That is the left-hand side, right? And then they tested 1, 2, 3, 4 light levels. So it's a foot candle because it's toward growers, but actually they put micromoles per square meter per second in here. It's hidden by the plants, but the shortest, the smallest value is 0.05 micromoles, 0.1, 1.0, 2.0. So it's a very low light, right? This classroom was what? Like 2 micromoles here, and then in under my Elmo, it was like, I don't remember, 10 or something like that, wasn't it? So it's very low light compared to outside. Outside, daytime max was 1,000 could be. Today, probably 1,200 or something like that. So compared to that, plants can sense very fine light. Good question. Okay, so here is the definition of the flowering response. Short day plants only flower or flower earlier when the photoperiod is less than some duration. And long day plants, opposite response. So day neutral, technically insensitive to photoperiod. And then flower in approximately the same time under the short day or long days, as long as other conditions are same, temperature. Okay, so the day neutral is supposed to be insensitive to the photoperiods. However, there's a confusing terminology, particularly for strawberry cultivars. They call day neutral without confirming actually they are day neutral. But those are the field crop. That's why they haven't done very precise testing like floriculture people do. But anyway, so those are the 3 classification. Yes?
So I know in the graph you showed us earlier for the short day plants, it was like 100% flowering at what looked like 0 for photoperiod, but is there some sort of like
In between.
photoperiod that like above above like, I don't know, 2 hours or something, it's 100% and then it follows the curve? Because it seems like even for a short day plant, they wouldn't flower at like 0 hours of photoperiod.
Oh, yeah. So the,
Minimum.
yeah. I think so. So, realistically, short day plants, yeah, so it's actually a good question you ask. So what's the short day plant's shortest photoperiod they can actually sense? I bet so plants use light for photosynthesis and then also use the light as a signal. And we are talking about photoperiodic response regarding the light as a signal. So if you go shorter and shorter days, then it actually reduces the photosynthetic light per day. So the DLI also declines. So plants cannot grow under that very small DLI. So you are testing photoperiod, but another factor is coming up. So it's very difficult to separate that very low photoperiods or very short photoperiods range. So I don't see, so that's why practically nobody tested that range. But if I see that, that's quite interesting.
So for the graph on there, it wouldn't start at 100%
Yeah.
at 0. It would kind of like start and then go up and then go down.
Or sort of that because we don't know that
Yeah.
short range. Yeah. So the question was the previous graph, oops. So for example, if you assume, this way, if you assume this is 0, then you really can't, extend the line to 100% because it's unrealistic to expect flowering at 0 photoperiod. So I don't know how this behave when it is getting closer. Probably goes down because growth is not, promoted. But where it is, I don't know. Yeah, it's a good question. All right. Okay. So that's that. Yeah, so now we talk about quantitative and qualitative response. Okay. So qualitative response is clear. Threshold and then greater than threshold flowers. That's long day plant response. Quantitative response, if you get the data at one point, like this, you might see lower percentage of flowering on the short day and then extending day lengths accelerate flowers. So when you see this kind of response, then that is called quantitative response. Basically what it means, plants flower anyway under any day lengths. However, if you have a longer day, then they flower more quickly. So the flowering response is promoted under longer day. So that's a quantitative long day plants. Okay, they flower anyway for quantitative plants. Qualitative plants, you got to cross the threshold line. Otherwise, flowering is not expected. So it's very different. So that's why I think qualitative plants is called obligate, long day plants in this case. And then quantitative long day plants is called facultative long day plants. Okay, the same response for the short day. The clear threshold is a qualitative response. And then more like a continuous, incremental response is a quantitative response. And then this is a short day plants. So qualitative short day plants, quantitative short day plants. All right? Okay. So if you see this type of table, it's probably easier to distinguish quantitative response and qualitative response. So this table is showing a bunch of different photoperiods tested. Species A and species B, sort of two different species. And then each one is showing the percent flowering, so how many plants, flowered at the end. and then also days to first flower, or days to see the majority of the plants flower, okay? So the first one is showing 0, 0, 0, and then data couldn't tell how many days it took, so basically it didn't flower, right? And then from 14 hours, 70%, 80%, 100%, it's not quite 100%, but the tendency is that there is a clear threshold in here, okay? And then days to get flowers is also, you know, it's infinite, and then meaning never flower, and then also here is 30 to 50 days to flower. That is a example of qualitative response, and then the lower in the table is quantitative response. Very different look. So 8 hours to 18 hours, basically they almost all flowered at the end, but how many days to get to the flowers is very different. So longer time for 8 hours, a little bit less time for 10 hours, less, 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 less. So obviously, longer day is accelerating flowering response, and that is quantitative response. Okay, the same thing, you know, can be seen in a short day response. So now you see, you know, different response, right? So you can classify short day plants, long day plants, quantitative response, qualitative response. Okay, it's not so difficult. Okay, are you with me? All right. Okay, good. All right, so there are, you know, just like I said, you know, DLI needs to be considered, blah, blah, blah. There are other factors triggering flowers of the plants. So this is a list of factors. Physiological age affects. Some plants just flower regardless at certain, you know, age or certain, after developing certain number of leaves, they flower anyway. And some plants responding very sensitively to the carbohydrate reserve, you know, how much energy in the body, so the vegetative, you know, growth, it's pretty much affecting flowering status. And temperature, some plants have an interaction, so that this range of temperature, they respond almost like a short day plants. This range of temperatures, they respond as a day neutral. So there are interactions between temperature and photoperiod. And then, of course, some plants require chilling before having the flowering response to the photoperiod. So it's just combination of chilling and photoperiod requirement or required. So that's, you know, particularly some of the floriculture species like that. So that's why some experiment, you know, usually researchers impose low temperature for certain weeks and then start testing for photoperiods. But anyway, because those plants require both as a signal. And then, yeah, photoperiod effect. So there are multiple factors. Therefore, we need to separate those factors when you test just photoperiodic response. And then again, requirements are species and cultivar specific. That's why, you know, floriculturists are busy finding out, you know, what is this new varieties coming up in the market, how growers can trigger flowering. So this one is quite important information. Not many people understanding that. This is appropriate way to design experiment to test photoperiodic response. So again, flowers can be triggered by other factors. So one thing we want to separate out is the effect of DLI, which is giving a total energy to develop vegetative growth and carbohydrate reserve, and photoperiod, which you really want to test. And then good thing is that, you know, the photoperiod can be sensed by plants even at very, very low light. So if you create artificial long day using very low light, then you can separate out the effects of DLI and then also photoperiod. So here is the Michigan State University's procedure, which actually my group is following right now to test some of the strawberry varieties. but certain hours of natural light per day just to give a chunk of DLI. And then that's uniform DLI across the treatments. And then either bringing the plants into the growth chamber or covered with opaque, blackout cloth, and then create artificial lighting conditions to extend the photoperiod. So the night hours in this case is a natural photoperiod plus 1 hour, 2 hours, 3 hours, up to 24 hours to create artificial long day, extended long day. And then if you do that, because it's only 2 micromoles in that chamber, the natural light doesn't come in. So the additional DLI, even 24 hours by 2 micromoles is very, very small. Okay, here's the exercise, if you remember. Micromoles per square meter per second is a ppf, all right? And then that's an instantaneous light intensity, okay? 2 micromoles per square meter per second. If that light intensity continues for 1 hour, what is the total amount of light per hour? Yeah, so 2 micromoles per second, and then if you provide that 2 micromoles per second for 1 hour, what is the total? 7,200 micromoles. That's correct, per square meter per hour. And then if you multiply, hours, so this condition, 1 hour just providing 7,200. So that means 0.007 more, right? Because a 7,200 is a 7.2 millimole, right? So that means 0.007 more. So it's only that small amount is added to the DLI. Okay? So that's why you can test the photoperiod without affecting DLI. All right. And if you look at the literatures of researchers testing photoperiods, they don't care the influence on the DLI, so they use a lot of light, 100 micromoles or 50 micromoles, and then extend the day lengths. And it's really not separating out DLI effect and the photoperiod effect. And then this group is the only one clearly mentioned that is not the way they want. Okay, so qualitative response and quantitative response, this is the definition. So plants only flower under particular photoperiod. That is the qualitative response. As an example, plant that only flowers under shorter photoperiods than a particular photoperiod. Okay? And quantitative response, that is plants flower under any photoperiod but flower faster under some particular photoperiod. For example, a plant that flowers under all day lengths but flowers earlier under longer days is a facultative long day plants. So you got that. Okay, so how do you control photoperiod in greenhouse? Extending day lengths is easy, right? Just put the lights on. Yeah. High pressure sodium lamp, which is a yellow lamp. When you come to the greenhouse area at night, yellow lamp, that's a high pressure sodium lamp. Or LEDs nowadays, or incandescent lamps, old technology but still reliable. Everyone uses that. So addition of artificial or electric lighting. And right now still incandescent light is most commonly used lighting, but they are shifting, okay, incandescent lamp to LEDs. Or more, efficient lighting. And then again, effective low light intensity is, I think that this is a recommended light intensity, although the previous slide shows that some of the plants can sense even much, much lower light intensity. But right now, as a sort of recommendation for growers, 2 to 3 micromoles light intensity is typical. And that's low enough, You really don't need much energy for that. Another quite interesting, way to create sort of pseudo long day condition is doing a night interruption. night interruption. So in the middle of the night, around midnight, put the lights on. So the sunrise and sunset are natural. So you go through the dark period, but basically breaking the long dark period into two, short dark periods. That's a night interruption. So why? So why it is actually associating with long day, extending day lengths. So it's something like that. So the night interruption, okay, night interruption. So it's actually making dark period shorter by night interruption. Remember, short day plants, actually, particularly short day plants, count the night lengths. Okay, so that they are responding to night lengths. There are lots of modern biology going on right now. So, but I try to simplify using classic understanding of plant physiology. But so plants are responding to day lengths, but actually sensing the night lengths. So the long day plants actually meaning short night plants. Okay, long day plants actually short night plants. So if I say plants flower at longer day lengths, that actually means plants flower at shorter night lengths. Okay? So if you break the night time into shorter pieces, because plants are sensing dark period rather than actual photoperiod. And then in that case, the flowering response happens. And so this one under short date, so this is a critical photoperiod, right? So longer than critical photoperiod, short day plants don't flower. Okay, shorter than critical photoperiod, right? Then flowers. Okay, the photoperiod is the same, but breaking the night time into short pieces. So that is basically creating similar situation as long day, even though the day length is the same. So that's why they don't flower. Okay. All right, even though the day length is shorter than critical. Same thing for long day plants. Longer day they flower, shorter day they don't flower. If you break, apply night interruption, because the night length is equivalent to the long day situation, therefore they flower, long day plants. Okay, so that is, applied to this night interruption technique a lot in floriculture, and you may see that greenhouse having lights in the middle of the day, middle of the night, or even in an open field. If you go to not California, if you go to Florida, chrysanthemum plants are propagated in Florida, open field, but lights are on. Okay, why? Because chrysanthemum, generally is short day plants. Okay, and in Florida, day length is already too short. Short enough to trigger flowers. Okay, this is a propagation facilities. You don't need flowers. You don't want flowers. You want more leaves and shoots and stems rather than flowers. Chrysanthemum have terminal flowers, right? So when you get flowers, then that's the end of growth. So you don't want to end the production by flowers. You want to continuously, stem and leaves. So to do that, they need long days, right? Then let's say the critical photoperiod is 14 hours. In Florida, it is difficult to get 14 hours natural light. So whether you extend the day length by night or night interruption in the middle of the day. So the night interruption is very effective for short day crop like this, because only a short, photoperiod or additional hours would affect. And then again, only a few micromoles. Then under that, the plants are continuously vegetative, growth. in the vegetative growth stage, so they can cut, cuttings and harvest cuttings and ship them to other greenhouses in the States, and they can finally flower. Okay. All right. So this is also showing the light intensity. So I'm gonna skip this. But recommendation is again 2 micromoles. This is my greenhouse strawberry. We have a quantitative long day plants, and they like long day. So to accelerate the photoperiodic response, therefore we put the lights on. In our case, instead of night interruption, we are just adding photoperiod, so the extension lighting. And then again, target intensity is 2 to 3 micromoles in our case. All right, so this one is a Campanula example. You saw 10, 12, 13, 14, 16, 24, and then this is the night interruption. What was the conditions? I think it was provided under short, so the 9 hours of natural light, and then 1 hour extension, 3 hours extension, blah, blah, blah. And then I believe this is just night interruption. So the natural day length is most likely 9 hours for this case. And then showing almost equivalent response to these long day situation. Yes?
For night interruption, how long would artificial lights have to be on in order to make it effective?
Good question. So how long the night interruption lighting should be to be very effective. So I see recommendation 4 hours. But I also know that the research done much shorter. But I think the grower's recommendation to assure the flowering response typically long enough, like 4 hours to assure.
It has to be greater than the threshold, the critical threshold, right?
But it's in the middle, so the threshold is in the dark side, dark period. So if adding 4 hours in the middle of maybe 18 hours of dark period, and then that means breaking up to 7 hours and 7 hours, right? The total is 18 hours. And then in that case, if 7 hours enough to consider as a short dark period to trigger long day response. Okay, that's complicated, huh? It's just so you have to switch, dark period and long day period, photo period back and forth. But that's how plants are responding. And then if you're interested much deeper in physiology, lot of information, probably plant physiology course, a graduate level of plant development course covers a lot of, which gene is involved and what cofactors, associating with gene and blah, blah, blah. So that's very much top-notch, the current biology, plant biology. So we did some journal club last year, but it's very complex, not well known yet, but a lot of studies done, particularly in Asian countries and European countries. There are researchers focusing on this flowering response, molecular level. That was interesting. Okay, so this one is another example. This is a night interruption again. Equivalent response to the extension lighting, and this is a night interruption. Okay, and this is what was that? Oh, this is so this is probably answering question to Caitlin. So this is a night interruption hours. So this is probably the base for recommending 4 hours. Because you can assure some of the plant's response by adding 4 hours. Okay. All right. So that's the day extension or long day treatment by using night interruption. So the opposite side, if you want to create short day, the only way to create short day in a greenhouse is just blocking light. There's no other way. It's more, I would say, challenging than long day treatment, because think about when short day is needed is under long day, right? So under long day, it's basically summertime. So in summertime, blocking greenhouse with blackout cloth, you can imagine it's gonna heat up the greenhouse. So that's a huge challenge. So usually growers do early in the morning, few hours, closing the curtains like this. So those are the blackout curtains. And then also at the end of the day, when sun is already, low, then pull the curtains again, and then make the total day length shorter.
But isn't it less expensive to do that than create artificial light? Like for example, doing a comparison between a short day and a long day plant. If a long day plant, you would spend more money creating artificial light than a short day plant doing all the covering of the greenhouse.
Yeah, so the question is about the cost, putting long day treatment for long day plants versus short day treatments for short day plants. Yeah, I think so. Lighting is always high expense. But when you block the light like this on the hot summer day, then you have to cool somehow, which is another expense, or lose the plants. So it's not really, electrical energy is, yeah, of course, high in lighting. But again, it's only 2 micromoles. But if it accumulates, I'll show you the number, but it's a lot of energy. Yes?
Also, if as low as 2 micromoles is enough to trigger the photoperiod to extend it, how do you get shading that blocks out so much?
Yeah. Yeah, the question is, how do you, assure the darkness? It's you have to exclude all the lights. Yeah, otherwise plants don't consider that as a dark period. So it's a very challenging technique to do that in long day conditions. So by the way, this is chrysanthemum pot mum production. Okay, so this greenhouse, they want flowers. They really want flowers, therefore they want short day. Okay, opposite to propagation situation. Propagation, they didn't want to flowers, therefore they created long day. Here they want flowers, therefore they put short day treatments. Ohio in summer, middle of summer, so it's very hot and humid.
I was just wondering how long, I guess, do those curtains last? Because I know I've had my curtains, and after a while they disintegrate.
Yeah, probably 3 years, 4 years, I guess. Yeah. Yeah, because it's UV. Okay.
What about if you had reflective curtains?
It might be reflective the other side. I don't know. Yeah.
Like the.
But still. Yeah. So it's still. I don't know. Next one shows. Yeah. No, it's black too. I think the selection is cost and impracticality. But it could be white and black, panda plastic type to cover, so that it reflects and maintain relatively cooler inside the enclosed, closure. So this is another example. This is a bench-based. So, floriculture challenge is you have so many plants in your production system, different response for different species. So some like to have long day, some don't like to have long day, so you got to deal with that. So whether you separate the greenhouses to do the treatment at once, or bench-based treatment like this. So it's really interesting, and they are practicing science-based knowledge by doing that. Okay, and photoperiodic response actually more, having interaction with temperature, and then also only certain photoperiods to trigger, not shorter than that, not longer than that. So it's just different responses for different species. So this is what scientists classified, and actually 25 different responses. And so it is very complex physiology, and growers are doing really well to look at the practical response and develop practical technique. But anyway, so I wish there's a much easier way to find it, because new varieties coming in every year and every year. And then if there is a sensor or something, just, check it out and then show, okay, this is a number 11 response type of thing. That would be much easier to develop technology. But anyway, so that's my sort of wish. And then you guys are new generation scientists, so you can probably help us in the future. Okay, yeah, so this is the one I was talking about. So the Florida situation, night interruption is used for suppressing flowers in short day plants instead of triggering flowers in to get much longer day. But this is a conventional use of lighting. Just responding to Enrique's question. So this is a traditional incandescent lamp based application. So they use 150 watt bulb per every 100 square feet. So that means 10 square meter area. So it's not high density, right? It's very low density lighting. Every 100 square feet, they have one bulb. But because of the huge operation, Florida chrysanthemum propagation is huge industry. And this one company, not the total of Florida, one company has to deal with 18,000 bulbs, 150 watt per bulb. So that it actually 2.7 megawatt operation. So it's a lot of energy. And then you know that incandescent lamp is very low efficient lighting because it generates a lot more in the heat, but not so much in the actual important light quality that plant can sense.
Is that 2.7 per night or per year, or how does that?
So it's a per second, 2.7 megawatt joule per second. Yeah, so if you use that for hour, 2.7 megawatt hour, and then the cost of that, how much is that? 10 cents or 15 cents per kilowatt hour. So you can compute how many dollars they are just using to make sure the flowers are not going to happen. It's a lot of energy. Yeah. Okay. So the developing light technology to replace incandescent lamps is it's very important. And then I'm in a group of developing greenhouse lighting technology. And my group is not working particularly to replace incandescent lamps, but floriculture group is working on that. So incandescent lamp is very inefficient, light bulb, 100-year-old technology. We are still using that technology. How many of you have incandescent lamps still at home? It's very cheap, right? Cheap and nice, but it doesn't last long, and it generates a lot of heat. So that means it's very inefficient. So the direction is going into a fluorescent tubes, and now it's going to LED lighting, more energy efficient. And then also, because of the inefficiency, some countries, and the US also decided to terminate this technology. However, horticulture industry is exempt, meaning they can use as long as they can, as long as they find the bulb. But I think the price is going to increase eventually because the market is shrinking. People are more encouraged to switch to more energy efficient light technology. So that's happening. So therefore it's a critical need to find out if we can use other type of lightings to trigger flowering response. Okay, flowering response is the photoperiodic response, but involves phytochrome. Phytochrome sense red and far red. Okay, and incandescent lamp is a very unique light quality in terms of 300 to 800, the plant biological active radiation. lot of far red. So this is an incandescent lamp scan. This is the energy or photon level, and then this is a 300 to 800 level, and lot of far red. And then there are a lot more infrared, longer, much longer wavelengths. But I'm just cutting off because 800 and greater, it's just the heat. We don't need that for plants. So, but anyway, the lot of far red and then good amount of red, and then yellow and a little bit of blue and green thing too. So that's incandescent lamp. So fluorescent tubes, this is a traditional cool white fluorescent tubes, and then other electric lights do not have usually far red component in it. 700 to 800 is a far red. Remember from the Wednesday lecture? Red is 600 to 700. Far red is 700 to 800. And then if you look at the spectrum of electric lighting, or not the incandescent, but the white lighting, it doesn't have far red. And why? Because our eyes don't respond too much to the far red. So adding far red in the light spectrum is waste of energy. But because of the old technology of incandescent lamp, it's a filament, it's sort of heating up, right? So that's why it just happened to have far red. So that's incandescent. But for plants, having far red is very important, okay? Because it's phytochrome. Again, Michigan State did a lot of work on the light quality for photoperiodic response, and several years ago they tested several species and several different lighting, cool white, compact fluorescent lamps, high pressure sodium, incandescent, and metal halide. So those lighting, we review the lighting technology, artificial or electric lighting technology in the later class lecture. But anyway, so those four sort of major lighting technologies they tested. So the earlier study showed that it doesn't matter, light quality doesn't matter, it flowers the same way. But this group re-examined, this finding, and then by introducing more different crop species, long day plants and short day plants. And then they discovered that, for example, petunia, which is long day plants, flower when incandescent bulbs is used, but didn't flower when cool white fluorescent tubes or lamps are used. So plants are, some of the plants, not all of them, are very sensitive to the light quality used for photoperiodic response. And then light quality specifically lacking far red is problematic. So they actually developed LED lighting bulbs, the screw-in type of lighting bulbs, but having a capacity to change the red and far red ratio, meaning the amount of red and amount of far red in the same bulb, and then tested a bunch of different red far red ratios to see which range of red and far red ratio is needed for the plant flowering response. Okay, phytochrome, if you remember Wednesday lecture, the form of phytochrome, two forms, far red absorbing and red absorbing, ratio of the two forms determined by the ratio of the ratio of the incident light, red and far red. Okay, so that's why they tested different red and far red ratio. So this is again petunia. This is Eric Ranko's slide from Michigan State. So the far right, we have 100% far red LEDs, and then in here, this column is 100% red LED treatments, and then this is the incandescent control, and this is short day negative control. Okay, so this is a positive control, and this is a negative control. So the positive control is a conventional system, therefore it flowers, and then it shows certain range. So this is 100% red LEDs, and then incrementally they added far red to the light bulb. So the red far red ratio is different. And as you can see, 100% far red didn't work to trigger flowers. 100 red didn't flower. And then a little bit of far red added, didn't flower. So there is a certain range worked pretty good. So that is suggesting both far red and red are needed for some species like petunia. Okay. All right. So yeah. So this is the flowering percentage, and this is the days to flower. So it looks like everything eventually flowered under these long day conditions created by different red and far red ratios lighting. But if you look at the time to flower, it's very slow and delayed under 100% far red, and then relatively delayed compared to the positive control. So 40 days versus 35. Few days difference is very critical in scheduling floriculture crops. So that's why we consider this is very important. By the way, these numbers, this is a PPE, this is a phytochrome photo equilibrium. So this is a value to quantify the quality of light in terms of plant response. So it's quite counterintuitive, quantifying the quality of the light. And then this is a value reported by this paper, photosynthetic efficiency and phytochrome photoequilibria, determining using spectral data. So this is a phytochrome red absorbing form, and this is a far red absorbing form. So those two, the absorbing spectral characteristic of absorbing specific wavebands of red absorbing and far red absorbing forms, you can actually weigh, and then estimate how much of the phytochrome is in the red absorbing form and how much of the phytochrome is far red absorbing form. Far red absorbing form is more functional, biologically active form, and then you can compute the value. So this is the value, and then the higher the value is, more activated phytochrome is. So that's sort of way to quantify the quality of the light. Okay? Any question? Okay, good. So it is really complex, but very important technology using that understanding.